In set theory, a discipline within mathematics, the aleph numbers are a sequence of numbers used to represent the cardinality of infinite sets. They are named after the symbol used to denote them, the Hebrew letter aleph. The cardinality of the natural numbers is, the next larger cardinality is aleph-one, then and so on. Continuing in this manner, it is possible to define a cardinal number for every ordinal number I plus or minus, as described below. The concept goes back to Georg Cantor, who defined the notion of cardinality and realized that infinite sets can have different cardinalities. The aleph numbers differ from the infinity commonly found in algebra and calculus. Alephs measure the sizes of sets. Infinity, on the other hand, is commonly defined as an extreme limit of the real number line, or an extreme point of the extended real number line. Aleph-naught is the cardinality of the set of all natural numbers, and is an infinite cardinal. The set of all finite ordinals, called I_ml or I_ml0, has cardinality. A set has cardinality if and only if it is countably infinite, that is, there is a bijection between it and the natural numbers. Examples of such sets are, the set of all square numbers, the set of all cubic numbers, the set of all fourth powers, the set of all perfect powers, the set of all prime powers, the set of all even numbers, the set of all odd numbers, the set of all prime numbers, the set of all composite numbers, the set of all integers, the set of all rational numbers, the set of all constructible numbers, the set of all algebraic numbers, the set of all computable numbers, the set of all definable numbers, the set of all binary strings of finite length, and the set of all finite subsets of any given countably infinite set. These infinite ordinals, I_ml, I_ml+1, I_ml2, I_ml2, I_ml and I_0 are among the countably infinite sets. For example, the sequence of all positive odd integers followed by all positive even integers, 1, 3, 5, 7, 9, 2, 4, 6, 8, 10, is an ordering of the set of positive integers. If the axiom of countable choice holds, then is smaller than any other infinite cardinal. Aleph-one is the cardinality of the set of all countable ordinal numbers, called I_ml1 or I_copyright. This I_ml1 is itself an ordinal number larger than all countable ones, so it is an uncountable set. Therefore is distinct from. The definition of implies that no cardinal number is between and. If the axiom of choice is used, it can be further proved that the class of cardinal numbers is totally ordered, and thus is the second smallest infinite cardinal number. Using AC we can show one of the most useful properties of the set I_ml1, any countable subset of I_ml1 has an upper bound in I_ml1. This fact is analogous to the situation in, every finite set of natural numbers has a maximum which is also a natural number, and finite unions of finite sets are finite. I_ml1 is actually a useful concept, if somewhat exotic sounding. An example application is closing with respect to countable operations. For example, trying to explicitly describe the I-Florin algebra generated by an arbitrary collection of subsets. This is harder than most explicit descriptions of generation in algebra because in those cases we only have to close with respect to finite operations so sums, products, and the like. The process involves defining, for each countable ordinal, via transfinite induction, a set by throwing in all possible countable unions and complements, and taking the union of all that over all of I_ml1. In popular books is sometimes incorrectly defined to be, but this is wrong if the continuum hypothesis fails. Continuum hypothesis. The cardinality of the set of real numbers is. It cannot be determined from ZFC where this number fits exactly in the aleph number hierarchy, but it follows from ZFC that the continuum hypothesis, CH, is equivalent to the identity. The CH states that there is no set whose cardinality is strictly between that of the integers and the real numbers. CH is independent of ZFC, it can be neither proven nor disproven within the context of that axiom system. That CH is consistent with ZFC was demonstrated by Kurt Paragraph Dell in 1940 when he showed that its negation is not a theorem of ZFC. that it is independent of ZFC was demonstrated by Paul Cohen in 1963 when he showed, conversely, that the CH itself is not a theorem of ZFC by the method of forcing. Aleph-I per mil, conventionally the smallest infinite ordinal is denoted I per mil, and the cardinal number is the least upper bound of. Among alephs, aleph-I per mil is the first uncountable cardinal number that can be demonstrated within Zumilo-Eurofrankel set theory not to be equal to the cardinality of the set of all real numbers. For any positive integer n we can consistently assume that, and moreover it is possible to assume as large as we like. We are only forced to avoid setting it to certain special cardinals with cofinality, meaning there is an unbounded function from to it. Aleph-I plus or minus for general I plus or minus, to define for arbitrary ordinal number, we must define the successor cardinal operation, which assigns to any cardinal number I the next larger well-ordered cardinal I plus. We can then define the aleph numbers as follows. And for I, an infinite limit ordinal, the I plus or minus th infinite initial ordinal is written. Its cardinality is written. In ZFC the function is a bijection between the ordinals and the infinite cardinals. Fixed points of omega, for any ordinal I plus or minus we have, in many cases is strictly greater than I plus or minus. For example, for any successor ordinal I plus or minus this holds. There are, however, some limit ordinals which are fixed points of the omega function, because of the fixed point lemma for normal functions. The first such is the limit of the sequence. Any weakly inaccessible cardinal is also a fixed point of the aleph function. This can be shown in ZFC as follows. Suppose is a weakly inaccessible cardinal. If were a successor ordinal, then would be a successor cardinal and hence not weakly inaccessible. If were a limit ordinal less than, then its cofinality would be less than and so would not be regular and thus not weakly inaccessible. Thus and consequently which makes it a fixed point. Role of axiom of choice, the cardinality of any infinite ordinal number is an aleph number. Every aleph is the cardinality of some ordinal. The least of these is its initial ordinal. Any set whose cardinality is an aleph is equinumerous with an ordinal and is thus well orderable. Each finite set is well orderable, but does not have an aleph as its cardinality. The assumption that the cardinality of each infinite set is an aleph number is equivalent over ZF to the existence of a well-ordering of every set, which in turn is equivalent to the axiom of choice. ZFC set theory, which includes the axiom of choice, implies that every infinite set has an aleph number as its cardinality, and thus the initial ordinals of the aleph numbers serve as a class of representatives for all possible infinite cardinal numbers. When cardinality is studied in ZF without the axiom of choice, it is no longer possible to prove that each infinite set has some aleph number as its cardinality. The sets whose cardinality is an aleph number are exactly the infinite sets that can be well ordered. The method of Scott's trick is sometimes used as an alternative way to construct representatives for cardinal numbers in the setting of ZF. For example, one can define card S to be the set of sets with the same cardinality as S of minimum possible rank. This has the property that card S equals card T, if and only if S and T have the same cardinality does not have the same cardinality of S in general, but all its elements do. See also, regular cardinal. References, notes. Sierpiewski, Wikia, Cardinal and Ordinal Numbers, Polska Akademia Nauk Monograph I Matematyk 34, Warsaw, Por STWOWE Wydornictwo Nauko, Mr. 0095787. External links, Haswinkel, Michiel, ed., Aleph 0, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4, Wellstein, Eric W., Aleph O, MathWorld.